exact time. Maybe. Yes. Okay. Can we see it?
We still cannot see, but we don't know if it's our fault or yours.
Are you sharing already, Johannes?
Can you see my screen?
No.
Okay. So a discontinuous percolation phase transition on the hierarchical lattice. Okay, so all yours. Thanks, Johannes.
Yes. So thanks for the introduction and thanks for the invitation. So as you can see, my talk is about like continuous and discontinuous phase transitions on the hierarchical lattice. So first, I would like to discuss actually like what is percolation, and then I will only like explain what are like phase transitions, and in particular continuous or discontinuous phase transitions. So for percolation, we will always start with a weighted graph G that consists out of some vertex set and the edge set, and we will always assume that the edge set is like sort of the set of possible edges. So between each two pairs of vertices, there's an edge between them. And now in percolation, edges can either be open or closed. And we're interested in the open component. So we're just interested in the open edges. And my rule for which edges are open is the following. So I have a weight that maps from E to 0 to infinity, and a parameter beta, which is greater or equal than 0. And now edges are open with probability. So this 1 minus e to the minus beta times j of e. So note that this here is approximately the same as beta times j of e. It's just that this here, of course, needs to be a probability. So choosing this 1 minus e to the minus is just a convenient choice to make sure that it's between 0 and 1.
Wait, Johannes, I think we can't see the bottom of your iPad. Only the first part.
Yes, so we see up to an HE
open with probability, and that's it.
Can you see more now or
no?
Okay.
Oh, yes.
Wait, maybe I need to go like in horizontal mode with the iPad. Is it better now or?
It's I think it.
Yeah, we see the examples, but from.
I think it's better.
Okay, let me check. No. Okay. Okay, so can you see now where I'm writing?
Probably not.
No, we don't. Independent of other edges, the last thing we see, I think.
Yeah.
Okay. Yeah, I think that's fine. So there's like nothing below that right now.
Okay.
Okay. So I wanted to say like for each pair of points, basically there's an open edge between them with this probability here. I will bother you. And this happens independently. I'm not seeing brightly because somehow it was okay until somehow you start speaking and it decided not to. So you just see the half, like vertical half.
And now we don't see the right part. Now it's cut vertically.
Okay.
Maybe like we're taking the iPad again. I don't know. Maybe that helps.
Okay.
No,
I'm really not sure what I should do now.
No,
it was perfect.
Yeah, now it's good. Now it's good.
Okay. So you can like the last thing to the right or to the bottom you can see right now is independent of other edges, I guess.
Yes.
Okay. Okay. So I have like this parameter beta and this function j. And so for each element in E, there's an open edge between them with this probability here. And if the edge is not open, then we say that the edge is closed. And what we're interested in is the open cluster. And I do this independently. So for each element in E, it's independent whether the edge is open or closed. So let's look at a few examples of this. Or maybe let me first say something here. So note that this function here is monotone. So it's monotone in both beta and j. So if you increase beta, then there's like a higher probability that the edges are open. And also when you increase j, there's a higher probability that the edge is open. So note that this function here only depends on beta times j. But the way to think about it is, so j is fixed and you vary beta. So that's why we write it like this. Okay, so let's look at a few examples. So for example, if the vertex set equals 1 to n and j of xy equals +1, then there's an open edge. So there's an open edge with probability p equals 1 minus e to the minus beta. And this is for each element in E. So in particular here, we see the open cluster is basically just the Erdős-Rényi Van Den graph. So here we see we have Erdős-Rényi, random graph. Okay, so that's example 1. So example 2 is maybe if the vertex set equals the integer lattice and the function j equals +1 for nearest neighbor edges and it equals 0 otherwise. So here the open cluster is just like nearest neighbor percolation. So we just have a reparametrization of nearest neighbor percolation with a different probability. So that's nearest neighbor bond percolation. With probability p equals 1 minus e to the minus beta. Okay, and the last example, what I want to discuss also for the rest of the talk is the following. The vertex set equals the integer lattice, and the function j is something that maybe decays polynomially with the Euclidean distance. So you can think when you have 2 points and they have a small Euclidean distance, then there's a high probability of an edge. And when they have a large Euclidean distance, there's only a small probability of an edge. So here, the open cluster might look something like this. So here, there's a picture in 1 dimension. So you have some like nearest neighbor edges, and then there you have some longer edges on top of this. And well, so you maybe see these very long edges. So maybe it might look something like this. And note, so what I draw here. So this here are the open edges that I draw. And these open edges, they occur exactly with this probability. So this occurs with probability p equals 1 minus e to the minus beta times j of e. Okay. So what we are interested in, or some assumption I will make right now. So we will work on the integer lattice, and we will assume that this function j is symmetric in the following sense. So it just depends on the Euclidean distance of its endpoints. So the function j of like the pair x and y is just a function of the Euclidean distance of its endpoints. And one question people in percolation theory are interested in is the following: does there exist an infinite open subgraph? So for example, if we go back to this picture here, so the question is, can you go to infinity, say starting from 0, only using the blue edges, so only using the open edges? And a few cases where this is known or how this holds. So for this, let's assume that f of n decays like n to the minus s. So we have this polynomial decay in the Euclidean distance. So first of all, there's always an infinite subgraph if this sum here is infinite and beta is positive. So if this sum here is infinite, then this basically guarantees us that the expected degree of the origin, which is just the sum over all x, the probability that 0 is connected to x is infinity. Okay, and then if the expected degree is infinity, just like the independence of different edges together with the Borel-Cantelli argument already tells us that the origin will be connected to infinitely many edges almost surely. So there are like these infinitely many blue lines that are attached to the origin. So clearly there's an infinite open subgraph. On the other hand, there's no infinite open subgraph if the sum here is finite and beta is less than the inverse of the sum. So why that? So if this sum is finite, then this, or if beta is less than the inverse of the sum, then one can easily show that this implies that the expected degree of the origin. So it's finite and it's even less than 1. And then if the expected degree of the origin is less than 1, by translation invariance, we also get that the expected degree of every other vertex is less than 1. And this already implies that there cannot be an infinite cluster, because you can dominate the branching, you can dominate the percolation with a subcritical branching process. On the other hand, so there is an infinite open cluster if the dimension is 2 or higher and beta is large enough. So that's just because if the dimension is 2 or higher and beta is large enough, at some point you will just like upper dominate nearest neighbor percolation in 2 dimensions. And you know, for percolation in 2 dimensions, there is an infinite open cluster when the inclusion probability of edges is high enough. So this here is like comparison with 2-dimensional nearest neighbor. And the last item is, yes, there's also an infinite open cluster if the dimension is 1 and J grows at least quadratically and beta is large. So this result is due to Newman and Schulman. This result is also optimal in the following sense. So if the dimension is 1 again and J of x decays faster than quadratically, then there's no infinite open cluster, no matter how large beta is. So this result is due to Aizenman and Newman. So also, this is quite interesting because here, this exactly characterizes in 1 dimension when we can have infinite open clusters or when we cannot have infinite open clusters. And also note that sort of we have a 1-dimensional system, but we can still have these infinite open clusters, and we can have them because we can like use these long edges to make these connections to infinity. So before I said that this property or this inclusion of edges is also something that increases with beta. So if you increase beta, then there's a higher probability that edges are open. And in particular, one can define the following. So one can define beta c, which is the critical value. So this is the smallest value for which an infinite open cluster exists. So here we have the smallest value for which the probability that there exists an infinite open cluster is 1. So note that this probability here, so the probability that there exists an infinite open cluster is always either 0 or 1. It's just by Kolmogorov's 0-1 law that it doesn't depend on finitely many edges, that this probability already needs to be either 0 or 1. Also by translation invariance, we can write this as the infimum over all beta, for which the origin is connected to infinity with positive probability. So here, this K0, these are all the x in set D, for which 0 is connected to x. And this means, so there exists an open path.
From 0 to x. Okay. And as I said before, because of
monotonicity, we can define this critical value. So note that this critical value in general is between 0 and plus infinity. So it also can be 0 and it can be plus infinity. So it's 0 exactly when we are in this case here. So when the expected degree equals plus infinity for every positive beta, then the critical value is 0. And it's the critical value beta c equals plus infinity if you're like in this case here. So if you have a model that does never have an infinite open cluster. But typically we are interested in percolation in the case where beta c is strictly between 0 and infinity. So when it's a positive real number. Okay, so one thing people in percolation theory are interested in is the behavior at criticality. So before we defined this quantity beta c as the critical value, and now we're interested in how does the system behave at criticality. And for this, I drew these two pictures here. So on the x-axis, we have beta, and on the y-axis, we have m of beta, which is just the percolation density. So it's the probability that the origin is in an infinite open cluster. And there are two possibilities. Either we have a continuous phase transition. So this means this function is continuous. So then it's 0 in this regime here. So when beta is less than beta c, and it's positive when beta is larger than beta c. And at this critical point, it's 0. So this is what people call a continuous phase transition. But there's also the possibility of a discontinuous phase transition, meaning that the function is 0 for beta less than beta c, and then it's positive when beta is larger than beta c, but this positivity here happens with some jump at the critical value.
So a few things I want to
say about this function. So this function m of beta, so first of all, it's always non-decreasing. So that's again just because of this monotonicity again. So if you increase beta, then it's like you add more and more open edges. So the probability that the origin is connected to infinity using open edges can only increase, but it can never decrease. It's also like relatively well known that the function is continuous outside of the critical point. So it's clear that it's 0 here, but then one can also show that it's continuous in these regimes when one is like bounded away from the critical point. And it's also always known that the function is continuous from the right. So it's always right-sided continuous. So in particular, if you look in this discontinuous phase transition case here, then if you zoom in, if you have a discontinuity, then the discontinuity, you know, this right-sided limit always gets attained at the point of discontinuity. So you approach here from the right, then you always get that m of beta c is larger than 0 if you have a discontinuous phase transition. So that's just because of this continuity from the right. Okay, and what I'm interested in now is the following. So we have the vertex set as the integer lattice, and the function j decays polynomially with the Euclidean distance. And now the question is, do we have a continuous or a discontinuous phase transition? And now let's discuss for which cases or when this is known.
So the question is behavior
at criticality for polynomial decay. So first of all, we have a continuous phase transition when S is between D and 2D. So this is a result due to Nornberger. So there's also a more recent proof of this fact by Tom Hutchcroft. So this result is also optimal, or this 2D here is also optimal, at least in one dimension, because when the dimension is 1 and S equals 2, then we have a discontinuous phase transition. So this result is due to Aizenman and Newman. So for all other cases of dimensions and S, it's conjectured that you have a continuous phase transition, and it's also known in some high dimensional cases. So for high dimensions, sometimes it's known that you have a continuous phase transition. Okay, so I want to zoom in a bit on this fact of the discontinuous phase transition, so this Aizenman and Newman result. So what exactly did they prove here? And maybe more importantly, how did they prove it?
So the vertex set, the theorem that the proof is
Following. So the vertex set equals the integer line now, and the function j behaves asymptotically like 1 divided by x minus y to the power 2. Then if you consider this limit here, so x goes to, so this limit of x squared times the probability that 0 and x are connected by an edge, and you multiply this with the percolation density squared, and this is either 0 or it's larger or equal than 1. And in particular, so you know that this quantity is positive. So you know that this whole quantity is positive for beta larger than beta c. So when you know that it's positive, when beta is larger than beta c, you can also deduce that it's even larger or equal than 1 for beta strictly larger than beta c. And then one can also use this right continuity, so the continuity of the right of this function m, to deduce that m of beta c needs to be greater or equal than 1 divided by the square root of this limit here. So this x squared times the probability of an edge. And from this, we know that it's greater than 0. And from this, one directly gets the discontinuous phase transition. Okay, and one thing, so it's also conjectured that at criticality, this inequality actually is an equality. So it's conjectured that for beta equals beta c, this is true. So this inequality here is an equality, but it's not known so far how to prove this, or it's not known so far if this holds. Okay, so one thing I want to discuss is why is s equals 2 a special value? So we see in one dimension, s equals 2 is special in two senses. So on the one side, it's special for the existence of phase transitions. So we see there are no phase transitions if we have faster decay. And we also saw that it's critical in the sense of continuity of phase transitions. So we have a discontinuous phase transition exactly for s equals 2. Okay, so let me focus a bit on why s equals 2 is a special value, and I'll try to explain how or why you have this discontinuity for s equals 2. So let's assume that the probability that x is connected to y is of order gamma divided by x minus y we have k between n and 2n. So that's something like this. So we have n here, 2n here, and k somewhere in the middle. And what we want to have now is that there's no open edge that spans over k. And we only consider the half line here. So we start at 0, and there's no open edge that has one endpoint in this interval and the other endpoint in this half line here, and that spans over k. So in other words, all open edges are more so either here or here, but no open edge over k. And for this, let's first compute the expected number of open edges that are over k. So if you compute the expected number of open edges, then we get the sum over, so x is less than k, and the sum over all y larger than k, the probability that x is connected to y. So that's just like a sort of linearity of expectation. So I sum over all possible endpoints of edges x here and y here, and that's the probability we have an edge from x to y. Okay, and then let's plug in this gamma divided by x minus y to the power 2. So we see that's approximately the sum over x less than k and y greater or equal than k, gamma divided by x minus y to the power 2, which is, well, at least approximately, when k is large, gamma times the logarithm of k. So this to the power 2 here is important because for all other values of s here, you would not get log of k, but you get this exactly for this power 2. And also we said that k is between n and 2n, so that's approximately the same as gamma times logarithm of n. So why is this interesting now? So we see that the probability that 0k is not connected to k to infinity. So that's just approximately e to the minus expected number of edges. So if you think like edges are, I mean, we know that edges are independent, and then the probability that there's no connection is approximately like e to the minus the expected number of connections. So we have e to the minus gamma times log of n.
Which behaves like n to the minus gamma. Okay, so for one specific k, there's only a
Small probability that there's a cut, so that there's this type of cut over k. So I guess I didn't say this before. So this here is what we call a cut. So if there's no open edge over k. Okay, but now let's count the expected number of cuts. So if we count the expected number of cuts between n and 2n, we just get n times, just like the linearity of expectation, that's approximately n times n to the minus gamma. So you have n many possibilities, and for each possibility, the probability of having a cut is approximately n to the minus gamma. So yeah, that's n to the 1 minus gamma. And here we see why I chose this gamma less than 1. So if gamma is less than 1, then the expected number of cuts is relatively big. So this just tells us something about the expectation, but then you can also like compute the second moment of the expected number of cuts. And what you can get from this is that the probability that there exists some cut in this interval from n to 2n is actually larger or equal than some constant which is positive. So there's a uniform positive probability of a cut in this interval from n to 2n. Okay. Okay, so can you still see that I'm writing? So
Yes. Yes.
oh, okay. I think there was some synchronization issue with my computer, maybe. So I think it should work again now.
You can see okay now. Yeah.
Okay, thanks for the feedback. So, and this like cut idea, one can also make a two-sided version out of this. So one can also look at the integer line. So the full integer line. And then one has like minus 2n here. minus n here, and maybe 2n here. And then we can look at the probability that one has two cuts. So one cut between like minus n and minus 2n, and another cut between n and 2n. And what one wants is there are like only edges that are like inside here or outside here, or also like from this like right to the left. But there's like the important thing that there's no edge from the inside to the outside. So these two cuts here means like no edge from the inside to the outside. And then if you compute the probability of this event, also the probability of this event is larger or equal than some other constant, which is also positive. And all of this works under this assumption that gamma is less than 1. And in particular, if you have something like this, then it's easy to show that you cannot have an infinite open cluster. Because like at every scale, there's just a positive probability that you cannot escape this scale anymore. So at like scale n, there's just a positive probability that you cannot use open edges to cross either from here like to the left or from here to the right. And if you cannot cross like either to the left or to the right, you just cannot go to infinity. And if this happens at every scale, then with like probability 1, it will also happen at infinitely many scales. So in particular, there's just some implication that goes like this. If gamma is less than 1, then there's no infinite cluster. So an infinite cluster just equals 0. And then there's like one argument due to Aizenman and Newman, which allowed to bootstrap this. So also if the probability being in an infinite open cluster squared times gamma, if this here is less than 1, then there's still no infinite cluster. So meaning again that this probability needs to be 0. Okay, and maybe the argument they used, so I will say one sentence about this. So the idea is if you have these long edges, then these long edges, you can only like use them. You can only use them to build clusters if you have large clusters on both sides of these long edges. Okay, so I had some like technical issues, so I'll
still see the screen.
Okay.
Yeah.
Okay. So last thing I drew was this here. So we have like long edges, and you can only use this long edge if you have like large clusters on both ends of this long edge. And this is like how to, or this is maybe one idea behind this implication here. Okay, so what I wanted to do in joint work with Tom Hutchcroft is to get a similar understanding of this phase transition phenomena for the hierarchical lattice. So let me first describe what actually is the hierarchical lattice. So formally it's defined as follows. So it's a group, and you can think of the group as like you have sequences in the torus, so infinitely long sequences, but all but finitely many elements of the sequences are 0. So that's the formal definition. And now for two elements in this group, I look at the largest I where the sequences differ. And then the norm or the metric or the distance between these elements is defined as L to the maximum I, so that xi is not equal to yi. So note that this here is finite because we know that each element in the group will be finitely, so xi will eventually just equal to 0. So also eventually these two quantities xi and yi will always be the same. Okay, so maybe let me describe a more intuitive definition of the hierarchical lattice. So what I didn't say so far, so the hierarchical lattice is also defined with respect to a side length L and a dimension D. And this is exactly like the side length of the torus and the dimension of the torus. And like one idea, or like how I imagine this, maybe with side length 3 and dimension 1 is as follows. So you start with one object, and then you sort of duplicate this object 3 times. So then you have like 3 types of this object, and then that's like the first level. So this here is like the first level, and now you align this in this one-dimensional setting. So then you have this object here, and you again duplicate it 3 times. So you have it 3 times and align it again into this one-dimensional line. So then you have this object here. So that's the second level. And then you do this again. So you again duplicate it 3 times, then you have 3 versions of it, and still put it again in a line. Then you get like this here with like 27 elements in total. So that's the third level. Okay, so and now what is the distance here? So the distance is the following. So I have another picture here. So so that's with side length 4, but everything else is the same. So if you have 2 points, A and B, then you just need to look. So to which level do you need to go until you are in the same, until the 2 points are in the same level. And then you need to raise like L to this power. For example, in this, so here A and B, so the side length is 4. Maybe let me write this here. Or it's here, so the side length is 4, and they're in the same first level. So the distance is just 4 to the power 1. So here A and B are not in the same first level, but in the same second level. So the distance is 16, which is 4 to the power 2. Okay, and I also drew this like tree structure above here. So you can also think of it goes up in this like tree-like manner. So you have 4 objects here, and then they form, you like copy this 4 times, and like with these 4 copies, they form this new object, which is like the next level. Okay, but itself, the hierarchical lattice is not a tree, so think of it more like as a metric space. So I also have this picture in dimension 2 here. So that's just the 2-dimensional version with side length L equals 2 and D equals 2 now. So again, you just take like 4 copies. So maybe you can think of you start with 1 point, and then you duplicate it like 4 times, and then you arrange them in this like 2-dimensional way. So you get this 1 square, and then again, you copy it 4 times, then you get this bigger square. So here it's 2, and here the distance, so this should not be 16, but actually should be 4. So it's like the side length of the largest block that contains both A and B. And maybe there's a question, is this even different? Or like, is it actually like the same object? And it's basically like almost the same. So this, as metric spaces, they're really similar because there just exists a bijection from this like one-dimensional hierarchical lattice with side length L to the D to the D-dimensional hierarchical lattice with side length L. So there exists this bijection, and this bijection is like sort of comparable to the matrix. So the matrix or the distances get distorted by this power of D. But in some sense, the dimension is fake, so you could always also just set the dimension to 1 and just think about the side length of the hierarchical lattice. Okay. So also one thing, so for this hierarchical lattice, I also wanted to like define the blocks or the balls of a certain radius. So that's just a notation. So lambda k of x, that's like the ball of radius L to the power k around x. So in particular, like lambda 0 of x would just be the ball of radius 1, which just equals like x itself. So that's like the 0th level. Then lambda 1 of x contains like the next level. So here it contains these 4 points. And then like, well, lambda 2 of x contains like even more points. So it's like these 16 points. And then like lambda 3 of x would contain like even more points. So the next 64 points and so on. That's just some notation. And I will also just write lambda k for like the box of side length L to the k around the element 0. Okay, so that's the definition of the hierarchical lattice. So I want to discuss like for what's percolation on the hierarchical lattice, or which results are known for existence of percolations on the hierarchical lattice. So we will work on the hierarchical lattice, and we'll still assume that this function j only depends on the metric on the hierarchical lattice now that we defined. And as before, the first question is, does there exist an infinite open subgraph? And sort of some of these conditions are just the same. So again, we have that if the expected degree equals infinity, so this happens also if and only if s is less or equal than the d. So if we assume here that this behaves like so x minus y to the power minus s. So under this assumption, we still have an infinite open subgraph just by the same argument as before. So this just tells us expected degree is infinity, and then Borel-Cantelli tells us that we can have this infinitely, we have this like stars that have this like just infinitely many open edges attached to them. Also, if beta is less than the inverse of the sum, this just tells us again that expected degree is less than 1, and then you can also dominate it again with some subcritical branching process. So it's more interesting if you have like polynomial decay with s is between, or s is larger than d. So here, Kowal, Meester, and Trapman proved that there is an infinite open cluster if s is between d and 2d and beta is large. But on the other hand, there's no infinite open cluster if s is larger or equal than 2d. Then also Dawson and Gorostisa improved this result. So they proved if the dimension is 1, I actually guess this dimension 1 is not important here. And the decay is like this. So you have a decay that's slower than log of the distance divided by x minus y to the power 2d, then you cannot have an infinite open cluster. And together with Tom Hutchcroft, I showed that this is optimal. So if the function j grows at least like log of the distance divided by x minus y to the power 2d and beta is large enough, then you actually have an infinite open cluster. So that's about the existence of phase transitions. So now about continuity of phase transitions. So the behavior at criticality. So also, so we have the same assumptions as before again. So this function x decays like the distance on the hierarchical lattice to the power minus s. And under this assumptions, Kowal, Meester, and Trapman proved that you have a continuous phase transition when s is between d and 2d. So together with Tom Hutchcroft, I showed you can improve this you have always a continuous function when this function j grows faster than this log of x minus y to the power x minus y to the power 2d. So as long as this function here decays not as fast as this function here, you have a continuous phase transition. So, but the proof really used basically the exact same methods as in this paper by Kowal, Meester, and Treadman. On the other hand, we also proved there's a discontinuous phase transition if the function j has exactly the same decay as this log x minus y to the x minus y to the power 2d. Okay, so I have like a comparison picture about one-dimensional line percolation versus one-dimensional hierarchical percolation. So the comparison is in the following sense. So for which profiles of decay does there exist a phase transition? Respectively, for which profiles do you have a continuous or discontinuous phase transition? So maybe let's first look at this top half here. So for the existence of a phase transition, we have on the one-dimensional line that this 1 divided by x squared is the critical value. So you have a phase transition when the function decays faster, so you have no phase transition when the function j decays faster than this critical profile, but you have a phase transition if it's at least this critical profile. And on the other hand, on the one-dimensional hierarchical lattice, this critical profile is now not 1 divided by x minus y to the power 2, but you have this extra log factor. So that's like different from one-dimensional to one-dimensional hierarchical, that you have this extra log factor. On the other hand, about the continuity or discontinuity of the phase transition. So for the one-dimensional version on the line, we know there's a continuous phase transition when s is between 1 and 2, and there's a discontinuous phase transition when j is, so when s equals exactly 2, so when we have exactly this type of decay here. And also we see something similar on the one-dimensional hierarchical version. So when j is exactly this critical profile, then we have a discontinuous phase transition. So this log divided by x minus y is exactly what we also see here and here. So when we're exactly at the lower critical dimension, then we have this discontinuous phase transition. And on the other hand, we have a continuous phase transition if you're like slightly away from this critical line. Okay, so next thing I want to discuss is, or maybe one word about how did we prove this continuity or discontinuity of the phase transition. So I told you before, there's this theorem / conjecture by Aizenman and Newman that this limit here, so this limit of x squared times the connection probability times the percolation probability squared, that's either 0 or it's bigger than 1. And it's conjecture that at criticality it's actually equal to 1. And on the hierarchical lattice, we have like a similar version of this theorem. So we have that this limit, now you have this extra log factor. And also you have the percolation probability squared. It's either 0 or it's larger than L. And here, so on the hierarchical lattice, we could even prove that this limit at criticality is exactly L. So it's something like you have this hierarchical. You should think this here is like a hierarchical version of this here. But at criticality, you even know that it's exactly saturated. But sort of the reason why we couldn't prove it for the one-dimensional line is that for like the hierarchical lattice just has so much more symmetries than the one-dimensional integer line. And using the symmetries, we could establish like this saturation of this inequality at criticality only for the hierarchical lattice. Okay, so the last thing I want to do is explain why is this log factor shows up. So why is this log x minus y divided by x minus y to the power 2 in some sense like a critical factor? So for the hierarchical lattice, ys equals 2d, respectively, y exactly this profile. And for this, let's first assume that we have some polynomial decay. So let's just do it in one dimension. So I said before, this like hierarchical spaces are always like in some sense isometric. So let's just assume we have the one-dimensional case. We had that the probability that x connects to y is of the form gamma divided by x minus y to the power 2. And now I want to give some argument that basically shows that you cannot have a phase transition. Okay, and the argument goes as follows. So what we do is we look at all x in lambda n and y which are not in lambda n. And we look at the probability that x is connected to y. So this is just something like the expected number of edges that go from scale n to scale outside of n. And just like by all the symmetries, that's just L to the n times the sum over all y, which are not in lambda n, the probability that 0 is connected to y. Okay, and then you should, like, you need to think about what's the best way to compute the sum. And so let's just write it like this. So that's L to the n times the sum k equals n plus 1 to infinity. And then you need to sum over all y in lambda k, which are not in lambda k minus 1. And then the probability of a connection. So this we know that's like gamma divided by y squared. So, okay, and then it's really just about finding out what's the value of the sum. So that's L to the n times so lambda k without lambda k minus 1. So this just consists out of L to L minus 1 copies of lambda k minus 1. So each of this has size L to the k minus 1. And the probability, or this gamma divided by y squared, is just gamma divided by L to the power 2k now. Okay, and now we get that's like L to the n minus 1 times the sum k equals n plus 1 to infinity. Okay, I think
Yeah, we lost your screen.
Yes. Okay, I'll try to reconnect again.
So I think
Now you should be able to see my screen again.
Yeah. Yes.
Okay, yeah, thanks for the feedback. Okay, so I said, so now it's just like, okay, well, you need to calculate the sum here. So you get L to the n, L minus 1 times gamma divided by L to the k. Okay, and this here is just like gamma divided by L. So that's just some constant. So in particular, there's just, so the probability that lambda n is not connected to the outside or to the complement is just greater or equal than some constant, which is positive. So there's just a positive probability, so a uniform positive probability that like one scale is not connected to the next scale. And then if you have something like this, again, with probability 1, there will be infinitely many n, such that this holds, so that the scale is not connected to the next scale. And then you cannot have infinite open path starting somewhere and going to infinity. So that's the case when we have exactly this function here. Now let's bring this log in. So if you have another term, like of this double logarithm, and now we need to assume that gamma is less than L, then, so let's just see how it changes in the calculation. So we get this other double log term here. So then we get this log term here. Okay, then see this is approximately this times logarithm of k, which is approximately the same as gamma divided by L times the logarithm of n. Okay, so in particular, it grows as n goes to infinity, and this here is not true anymore. But one still gets that the probability the probability that lambda n is not connected to the next scale, so that's greater or equal than n to the minus like gamma divided. It's greater or equal than e to the minus gamma divided by L logarithm of n, which is n to the minus gamma divided by L. Okay, so this is small when n goes to infinity. And now, so here we assume that gamma is less than L. So in particular, this here is less than 1. And now if you take the sum over different n,
then we still get infinity
here. Okay, now the idea is, well, if this sum equals infinity, then you still get like this event for infinitely many n. So it would be clear if the events were independent. So in this case, the events are not independent, but they're sort of almost independent. So you can still, like, in some sense, basically apply the standard Borel-Cantelli argument and show that one scale is not connected to the next scale for infinitely many n with probability 1. So this implies the following implication. So it's like similar to this technique of Aizenman and Newman. So if probability x is connected to y, this behaves like gamma divided by x minus y times this double logarithmic term with some gamma less than L. Then one can deduce that there's no infinite cluster. So the probability origin is infinite open cluster just equals 0. And like similar to the Aizenman and Newman technique, one can also bring in the other factor of the percolation density squared. So one can also show that this probability 0 is an infinite open cluster squared times the probability of a connection. So if this behaves like gamma divided by x minus y to the power 2 times the double logarithm of x minus y with gamma less than L, then one can also deduce that one actually cannot have an infinite open cluster. And so this is the main idea how we prove this discontinuity of the phase transition. Okay, so thank you. So I'll stop here. Thank you.
Thank you, Johannes. Any questions? So I had a question here. So can you do this stuff for FK cluster, like FK percolation?
Yeah, I think
Similar statements should hold for FK percolation, because I guess on the one-dimensional line, there's also this other paper. So there's this paper by Aizenman and Newman, which I cited quite a lot, and there's this other paper by, I think it's Aizenman, Chase, and Newman, where they do like this discontinuity of the phase transition on the one-dimensional, like long-range version. And I think that similar statements should also hold on the one-dimensional hierarchical version, but I'm not 100% sure.
But the proof idea of Duménil-Copin Garbantation does not apply here, I guess, right? Like renormalization and so it's quite different, quite much simpler, I would say, than the original Aizenman-Schulman argument, right?
Yeah, I think so, but I mean I think this Duménil-Copin Garbantation, it's mostly I think that or what I very much liked about is the case how they show the existence of the phase transitions. And yeah, there I'm not sure if.
But they as Avelio said, they transfer it to FK percolation, which I don't know. So you can do it here as well then?
I guess some results should hold for FK percolation, but I'm not exactly sure what the correct statement would be.
Okay, thank you.
Any other questions? Maybe in the chat. I have a question, but you go on and I can take a look at it. Yeah, I don't know how this works. Yeah, I can do it. Okay. So I have a question. So you showed us that basically, like one-dimensional, like line, long-range percolation, and the hierarchical lattice somehow are qualitatively the same. I mean, you have this log extra factor, but they're the same as with respect to the phase transition. Is there any aspect of the phase transition in which you know or you suspect that they could be different somehow? Like qualitatively different?
I think I'm not exactly sure. I think in like the most aspects, they should behave really similar. So if you consider like, for example, this percolation critical exponents, the one-dimensional and the hierarchical, one-dimensional hierarchical should have the same percolation critical exponents as sense like 2-point functions and like whatever cluster size decay and so on. But I'm not so sure if you consider so there's this other transition which is like a transition from non-mean field to mean field behavior, which happens at like s equals 4 divided by 3, and like at exactly this value, I think there's the conjecture is that some like log powers in the exponents are not the same for the like hierarchical for the 2-point functions and so on. But yeah, it's only like a very subtle difference about this precise asymptotics of the 2-point functions for s equals 4 over 3.
Do you want to ask something else? No. And then I have one more question. So in the end, in your, I guess your final slide, so you mentioned that, okay, you have these things for gamma less than L. So what can you say for gamma larger or equal than L?
So we can just
show that there exists an infinite open cluster.
Okay.
So yeah, for gamma less than L, sort of we show there can never exist an infinite open cluster, but for gamma greater or equal than L, we have a proof that you can have an infinite open cluster. And this is also essential in this, say, the saturation of the hierarchical Aizenman-Newman inequality. that we sort of can show that the critical value at, that this inequality is saturated at criticality.
No. Okay. So if there are no more questions, we thank Johannes again.
Thanks for the invitation.
And I guess